Right, as I've said, the alternator consists of the alternator, the rotating part, and the resistance of the armature, and the synchronous reactance, which comprises of XR, which is our armature reactance, and XL is the leakage reactance. Then we can say that the induced EMF is equal to V plus IA at an angle plus or minus phi times ZS angle beta. There we have a definition of our terms. And now if we take a leading power factor, that means the reference is there, which is V, leading power factor, angle phi. So therefore, IR always in phase with the current causing it, and IX is perpendicular to the current causing it. You remember this from in a capacitive circuit, the current leads the voltage, and in inductive circuit, the voltage leads the current. So that's the voltage. If you should do it like that, and there's IA and IAXS. And remember, it always rotates anti-clockwise, so therefore the voltage leads the current. This is again IZ, and that gives us delta. And that is E. Here you can see with a lagging power factor, E is bigger than V. With a leading power factor, E is smaller than V. Then we get a case where we have unity power factor. That is where the current is in phase with the voltage. Let's say that's IA. Then we have IA, RA, and IA, XS. Again, that is IZS. And then we have load angle there. Okay. So remember, for all, come on. For alternators, delta is always positive. Okay. Right. Now, we can determine the voltage regulation. Now, there are two methods that we are going to discuss, which is the synchronous impedance method and Rother's method. Right. Now, once we have ZS is given, power factor given, then we can say that E angle delta is V angle 0 plus or minus IA angle plus or minus phi times ZS angle beta. Then voltage regulation is equal to E minus V divided by V. Right. That's the easy part. We get Rother's method, which is a little bit more complicated, but not much though. There we need two graphs. An open circuit graph, which is IF against that, usually does something like that. And then we have short circuit characteristic. Né? Here we have IA against I field. That's usually a straight line. Okay, now we can start by saying E Rother is equal to V plus IA RA cos phi. There we don't need any angles, so that's an arithmetic sum. Okay. Now, the first thing is then, from E Rother, we go to the graph and say, okay, E Rother is there. And this is the excitation that caused it. So now we want to know, for the same excitation, what is the current? That'll be I short circuit. So then we can say that ZS is equal to V over I, but at the same excitation. Then now we've got the current that causes full load and the current that causes in the rated voltage. So I resultant will be I, let's call it open circuit at an angle 0 plus I short circuit at an angle 90 plus or minus phi. So now we go back to the graph and say, okay, I raise is, let's say, there. And then we read off what is the highest Rother, and that will be E resultant. And therefore we can say the voltage regulation is equal to the resultant EMF minus V over V. Now sometimes we draw the graphs on the same graph. So let's say that's I field. On this side, we have the induced EMF. And on this side, we have the short circuit current. So still, we get the same thing there and there. So now, if we go to full load, let's say I full load, then we get a certain excitation, which is that one. And now if we go straight up, that will be the voltage that gives rated voltage. But if you prefer, you can use two different graphs. It doesn't really matter. Now let's look at an example. Okay, this is normally what a problem looks like. The following data was collected during open and short circuit test on a 30 kVA 440 volt 50 Hz 3-phase star connected alternator. Then we've got the induced EMF with the excitations that cause it and the short circuit current. Right, let's look at that. So now we know it's a 30 kVA 440 volt star connected. We are always working with that. So we can calculate I full load. That is A divided by square root 3 V line. Eh? So that's 30 divided by square root 3 divided by 440. Okay, if you want to see that. That gives us 39.36. Make it 37. Okay. Now they want us to calculate power factor is 0.75 leading. Right, now first of all, you are going to draw this graph with the data given. Right? Now let's say we calculate now E Rother. That is V plus IA RA equals 5. So 440 on a line voltage, what's the phase voltage going to be? 213, eh? Plus 39.37. And the armature resistance given as 0.3 ohm. So then times 0.3 times 0.75.
Sorry, sir, where do you get the 231?
That's the phase voltage at 440. Remember, 440 is line, and V phase is MOS, V line divided by square root 3. So that's 440 divided by square root 3. That should give you 231.
I'm getting 254, sir. 0.3.
254?
Yes, sir.
Okay. 254. Yeah, you're right. My memory is not so good anymore. All right, so 254.3.75 plus 254. That's 266.59. So make it 266.6. So now you're going to your graph. Now if you've drawn it nicely, 266 is around about, let's say 7.5. So now there's our graph. And we find that for 266, the excitation was, let's say 7.5. And then if we draw our short circuit graph on that side, I short circuit, All right, that's the induced EMF, and this is the field current. Now, we said that, okay, 39,37. If you look there, that's almost 40 now. So therefore, for the amps, you get an excitation of 7. Right, so what now? The resultant MMF is the MMF that causes full load voltage, angle 0, plus excitation for full load current, angle 90 plus or minus 5. So that means we have 7,5 angle 0 plus 7 angle 90 plus 0.75, 41.4. Okay, so let's add 7.5, then angle 0, and then we add 7 at an angle of 131.4. That gives us 6 at an angle of 61. So now we go back to the graph. Now find E-res. So now we go to 6. We go straight up. And we find the voltage there. Okay, now let me just write them a bit clearer. That one was 7, this one is 6. So now, fortunately, we have a voltage there at 6. So, this is going to be right. Probably. So therefore, it is 229 minus 254 divided by 254. That gives us minus 9,84. Now, what do you see from this? This means that E is smaller than V, which we said for a leading power factor, E will be less than V. Right. That is the Rothert method. Now they say, all right, use the synchronous impedance method. So first of all, we have to calculate ZS. Now, normally we do that at the same excitation. Okay, let's use 254 because that's the excitation and the voltage. So that means it's going to be V over R over Z, R over I. That means it's 254 divided by 40. It's about 6 something. 6,35. And they've given us R, so beta, our impedance angle is R cos R over Z. That means it's R cos, 3 divided by 6,35. That gives us a 87.3. Okay, now E angle delta is V plus IA plus or minus phi. Oh, come on. Times Z is angle beta. So we have 254 plus, what was the current? 40 amps. At a leading power factor of 0.75, which was 41,4 times 6,35, an angle of 87.3. So 254, we add 40, an angle of 41.4, and 6.35, angle 87. Times it, and plus, gives us 220. An angle of 64. So the voltage regulation is 220 minus 254 over 254. That gives us minus 13%. Now, Rothert is optimistic and synchronous impedance is pessimistic. Now, the true regulation lies somewhere between these 2 points. Now, fortunately, these are quite close. Let's say 10 and 13. So somewhere in between those values lies our true voltage regulation. Now, basically all these problems look the same. We'll always get a short circuit characteristic and an open circuit characteristic with its field currents. And then you do exactly as what we've done here. First of all, you calculate your full load current. Then you calculate Rothert voltage. Then you go to your graph and see what is the excitation. And then you look up your full load current. What's the excitation there? Then you get the resultant current is the one that gives you rated voltage at an angle of 0 plus your short circuit current, 90 plus or minus phi. Then once you've got that, you go back to your graph, you go up, and you find what is the voltage there. That will be E res. You think you will be able to manage this?
Yes, sir.
Good.
So can you please send us some question papers and memos if you have?
I really don't. What I can do is,
Sir,
yes.
in terms of the graph that you have drawn there, since you are saying that we must, when we want the value of E-res,
Yeah.
we must take it down there and then move to the, according to the graph. Okay, how would we, is this graph going to be given, drawn for us in the test or what?
No, you'll have to draw it yourself.
How can our values be precisely correct, sir?
I mean, that'll be the same. I'm also going to draw it by hand. So
But the shape of the graph, say, the shape of the graph, how will we be able to draw the shape of the graph without not knowing the points of drawing it?
no, you will given this values. That is the values that you use to draw the graph.
Okay.
For 2, you go to 90. 4, you go to 166. 6 to 29.
Okay.
And then for the short circuit, 2, 11. There you actually need only 1 point because it's a straight line. So it goes from the origin straight up.
Okay.
All right. Just try the graph now, later on tonight. But I'll say this is basically the paper that we are doing in advanced diploma. So if you want to take a photograph, or will you be able to do that on YouTube? Let's go there, and then the second question you can rather leave, number 10. That's a bit higher grade for you. And the other one, those two are exactly basically the same. So I think if you're fine with that, clean through each other now, man.
Sir,
Yes.
when can we get the recordings for the session?
Well, I'll send it to you just now. When I've uploaded it, I will publish it on the group. All right, we've got less than a minute, then we must join again. So we'll carry on with this after the break. But you'll see that's basically the recipe. Froth it, then you go back and to see what causes it. And then you look for the resultant, which is the excitation that gives you full load voltage, plus the short circuit current, or field current